Great, so welcome back, and let's continue. So today is the lecture 5, and before that, as usual, we will have the Bayesian warm-up. So think about for a minute what we have learned, what we have discussed from the last time. So just give you 10 seconds, and you can think about it, and I will just tell you, have a general overall review of what we have learned. So the last lecture, we talked about probabilities, right? So probabilities is it is a number by definition between 0 and 1, and it has a property that if we consider all the possible outcomes and summing up all those possible outcomes, the probability up, it is sum up to 1. So we have the coin example, for example, there is a 0.5, 50% chance the coin is facing up, and then another 50% chance the coin is facing down. And then we add up 0.5 and 0.5, we get 1. And in the dice example, if we throw a dice and then the probability of one number facing up is 1/6, there are in total 6 possible outcomes, 1, 2, 3 until 6. And then if we sum everything up, we got 1 again. And then we talked about probability functions. And then there are 2 types of probability functions, depends on the type of the outcome. So is the type of the outcome continuous, or is the type of the outcome discrete? So in the case of a discrete data type, we talk about probability mass function. And if the type of the data, the type of the outcome is continuous, we talk about probability density function. And associated with the probability density function, there is another one, which is called the cumulative density function. So the PDF is the probability density function, and then the CDF is the cumulative density function. Both of the PDF and the CDF, they are used for the continuous, the data type. And then remember, in the case of a normal distribution, the PDF is the common bell shape we are familiar with, and then the CDF is a increasing sigmoid S-shaped line, so similar to the logistic curve. And then this is the cumulative density function of the normal distribution. So then we moved on to some discussion when we have multiple events. We used the example of being raining and being cold. So the probability of cold and raining, it is a joint probability, right? The two, they happen together or not happen together. And when we have multiple events, so joint probability is the joint probability taken together or every possible outcome of the events. And then we could also consider the marginal probability, which is you focus on one event and then irrespective of another one. So we can talk about the probability of being cold. It is a marginal probability, marginalized whether it is raining or not. I do not really care if it is raining or not raining. I just want to know what is the probability of being cold. And the third probability is the conditional probability. So there is a little bar in the parentheses. So it's written, it's read as probability of A given B. So P of A given B. So P of A given B is it is the conditional probability. B, so the letter B behind the vertical bar, it is the condition. So conditional on B, what is the probability of A? And we also talked about a few examples of joint probability, marginal probability, and conditional probability using 2 types of data. So one is, again, the discrete data type. Another one is the continuous data type. So we saw some tables and curves so that we could, so that we had a better understanding what each of the 3 probability means. Good. And then the last thing before we finish the last time is that we talked about the Bayesian formula. So the Bayesian formula is basically trying to describe the conditional probability of A and B, so one way or another, right? So we know how this probability works, and then it's very straightforward to derive the Bayesian formula. So today we will dive a little bit more of the Bayesian formula, so how to use it in our sense, how we can use it for some kind of modeling, because this is the purpose of the seminar. Okay, so today this topic is about linking data and the parameter. So here, this is the Bayesian formula. So we know that the left-hand side, it is probability of A given B equals here, right-hand side, the nominator is probability of B given A multiplied with P of A, and then the entire product is then divided by P of B, okay? So this is the formula, and we know that these letters, A and B, they are just something arbitrary. A can be something else, B can be also something else. So what about just replace A and B with something called theta and D? So then we could have the formula written like this. The shape is exactly the same, just that the letters are different now. But we can give some meanings to theta, and we can give some meanings to data. So theta, we can say it is parameter. It is something unknown, and it is something that we are interested in. We want to estimate. And then D, the capital D is data, is the observed data from experiment, from survey, from whatever we can collect, okay? And then there are also names to each of the four parts in this Bayesian equation. We know that there are four elements. Here, P of theta given D. Here, P of D given theta. Here, P of theta. The last one is P of D. So there are four probabilities, four of P. And so what are the names? So how they are called? How are they called in the sense of Bayesian statistics? So this one, the left-hand side, it is called the posterior. Posterior means how plausible is our parameter given the observed data. So it's quite straightforward in the sense that because this is a conditional probability, right? Given D, what is the probability of the unknown parameter? So this is posterior. After we have observed the data, so then it is called a posterior distribution or probability. So relative to the posterior, we have something called prior. Prior, then if you understand posterior, prior then basically means some knowledge we have before the data collection. So here it says how plausible is our parameter before observing the data. You see here, this is not a conditional probability. It doesn't condition on data, it doesn't condition on anything, just the P of theta. So this is the prior knowledge we have a priori prior to the data collection, prior to what we have observed the data. And then here, another one on the nominator, it is called likelihood. So here's P of D given theta. So we will discuss a little bit more about the likelihood, but here this simple definition says so how plausible is the data given our parameter is true. So the shape here, it is also something conditional, right? So here there's a little bar here, and the theta is the condition you can imagine, and then the D is here, and then you can imagine what is the P of D given some parameter. So here I repeat again, so how plausible is the data, P of data, given the parameter is true, And then the last one, the denominator, here P of D, it is called evidence, and it's P of data. So how plausible is the data under all possible parameters? Okay, so this one is quite tricky to understand, but let's leave it for the next slides. So here, it is the overall introduction of the names, the terms in the Bayesian equation, the posterior, likelihood, prior, and evidence. And then from the next slides, I will just talk about each of the four elements one by one. The first one is this. So what is P of data given theta? And if you recall how it is termed, it is the likelihood. So this is the model part. The likelihood is basically the model part. The model part is basically means how you would like to connect the known data and the unknown parameter. Okay. But you have to be extra careful in the sense that if this is a probability, and when this is a probability, then the theta part is fixed, right? So then this one is changing, okay? And in this case, if we have observed some data, then the data is fixed, and then the theta changes. So then we could make some claim that this likelihood, even though it is written in this form, you can read it as P of theta given theta, but it is not a probability function. So this is really confusing, and I will tell you a little bit more detail using one example. So to falsify the idea that this is a probability, we can use one of the property of probability. So if we have multiple outcomes, if we sum up the probabilities of all those outcomes, there should be one. And then in this case, this is a probability. But in this likelihood case, if we do this summing up, you see that it is not one if we sum everything up. And then in this case, the likelihood is not a probability. Okay, this is very abstract. I am aware of that. And let's use one example to illustrate this idea. So suppose we have two coins, and suppose we have one coin. One coin is enough. And then we do the coin flipping twice, okay? So suppose we have the coin, we flip it once and catch, twice and catch, and then we can record the results. If that is a head or is that a tail? So there are only 3 types of outcomes in total. So 0 means out of the two times of coin flipping, no heads facing up, just tail, right? And then here, this column, it means one head, one tail. Doesn't matter the order. It can be head, tail. It can also be tail, head. So this is another possible outcome after the 2 times of experiments. And then this column means the 2 times of experiments, head, head, throw, catch, head, throw, catch, and another head, okay? So those 3 columns, they are the possible outcomes of the 2 times of coin flipping. So those are the possible data we could have. And suppose that we have different coins, and we have, let's say, 6 coins. And for these 6 coins, for each of them, we do twice of the experiments. And what is different of the 6 coins is that the probability of each coin landing heads up, theta, they differ. So this probability, they differ. So for the first coin, if this probability is 0, so then this coin, if you throw it up and then catch it, it will never land heads facing up, because the probability heads up is 0. It's always tail. If you do 10 times of experiments, 10 times of coin flipping, it will just be simply 10 times of tail, right? 10 times of that. And then in this case, if we could write down the probability of these 3 types of outcome, is that we will always receive a 0 time of head facing up, always tail, okay, always tail. And then if we understand this part, then it's easy also to understand this one. So this one means this coin, there's another coin, and then the probability of facing up is 100%. So then we will always observe a heads up. So in this 2 time of experiment case, this is not possible, this is not possible, so only this one is possible 100%, okay? And then in the middle, there are different coins. So the probability of heads facing up can be 20%, and then this one is 40%, this one is 60%, this one is 80%, okay? So if you know the detail, and this probability actually follows this distribution, okay? And you do not even have to worry about that. You can just calculate simply by calculating the probability using this number. So if the probability of one time of heads up is 0.2, 20%, then what is the chance that you observe a consecutive head? So then you use 0.2 multiply with 0.2, you get 0.4, or 0.04, right? This. And similarly, this number is also easy to get. So probability of face up, of head facing up is 0.2. Then the probability of tail facing up is 0.8. So you can multiply 0.8 with 0.8. You get this number. Good. And then this number is 1 minus the other two. You get the probability of one head, one tail. And then we can do this calculation here for all the other coins, and then we can fill in up this table. So every number in this cell, I think it is quite easy to understand up to this point after the explanation, I guess. Okay, so now what we do is we will focus on the margin. We first focus on the margin here. The total number of probability here, this is always 1, and this is good. This also makes sense, right? So if the probability is 0, so given probability is 0, what is the chance that no heads face up? Given this is 0, what is the chance that one heads facing up? Given theta is 0, what is the chance that 2 heads facing up? And this is the same coin, and you flip it, and then you catch it. You record the outcome, and then if you sum them up, it is 1. Okay, good. And then here, also the parameter is fixed, so the theta is fixed. Given the theta is 2, given the theta is 0.2, is 20%. So what is the chance that no heads facing up? What is the chance one head facing up? What is the chance 2 heads facing up? Okay, again, the same coin. So given these conditions, what is the chance that each of the 3 outcomes happens? And then this total summary is 1. Okay, and then if we move down here, 0.4, 0.6, 0.8, and 1, so everything, they follow the same rule. So they sum up to 1. So I was trying to use the word when the theta is fixed. So when this parameter is fixed, and then the outcome varies, right? So when this one is fixed, here is 0, here is 1, here is 2, and then we sum them up, and the total number is 1. So the generic term is that the theta is fixed. We have 3 possible outcomes. We can say theta 1, theta 2, theta 3. So then the generic term is probability of theta 1 given the theta, probability of theta 2 given the theta, probability of theta 3 given the theta. So the theta, the parameter is always fixed, and then the data is changing from theta 1 to theta 2 to theta 3. And then in sum this up, it is 1. So then this is a probability, okay? And then the trickier part, it is the likelihood. So it also written this way, but now in this case, as I said here, now this makes sense. So the data is fixed, okay? And then the theta varies. So what that means? That means when we have a experiment, let's say we just do this coin flipping twice, and we just observe 0 heads up. And then the data collection is finished. We're not allowed to do further experiments, and then we only have this observation, tail, tail. We only have this, and then this is fixed. We cannot change it, so this is fixed. So what is the likelihood that the coin here, the theta, what is likelihood? So what is the likelihood that the coin is a fair coin. So this is something you want to infer, right? So the theta is changing. So here, when we have the data, this is fixed. We could, using the same equation, to calculate the likelihood. Okay, good. So those parts, column-wise, so those are the likelihood. So the data is fixed, and then the theta is changing. So the generic term is that there is theta 1, theta 2, theta 3, theta 4, until theta 6 in this case. So the P, the data part is fixed. So then this term, in the generic term, is P of the same data given theta 1, P of the same data given theta 2, P of the data given theta 3. So that the theta is changing, is different. The data is always fixed. We observe it, it's there, and then it is fixed. And then if we sum up all those numbers, P of data given theta 1, P of data given theta 2, P of data given theta 6, and then those 6 numbers in this case, you see here, it is not summing up to 1, okay? And then as well, here is not, here is also not. So in this case, the likelihood part in the Bayesian equation, it is not a probability, okay? It is not a probability. So this is still confusing, I guess, in the sense that if I give you something called P of data given theta, if you don't know if that is probability or likelihood, so you just cannot really infer if is that a probability or not. So the idea is that if for whatever reason you see a term called P of data given theta, if you have to know the place where it appears. So if you know that the theta is fixed and then the data is changing, then this is a probability because this is something we have seen here. But if we know that if the data is fixed but the theta is changing, then it is not a probability. So it depends on the purpose, depends on how you use it. So it depends on which part is fixed and which part is varying. Okay, good. And then to make it clearer, and some statisticians and researchers, they realized this confusion. They changed the term of likelihood, not the name, but how to express it in equation. So sometimes you see in the literature, they say L, there's a capital L of theta given data. So I do not have it on the slide, but you just say L of theta given data, okay? So probability is a function of data given theta, and the likelihood is a function of theta given data. So the changing part is different, and the fixing part is also different. It's basically the opposite. Okay, question. P of theta given data means the data is fixed and the theta varies, or is it referring to P of theta given data? Yeah, you are a little bit confused now. Yes, everyone is, I guess. I thought that the real parts in the bracket means that the aspect is given, like theta in P of theta given theta. Yeah. Well, after the explanation, are you better? Do you feel better? Do you understand better? So it is written this way. It is written this way. But in the Bayesian equation, here, this is not changing. So here the data, and this is changing. Yeah. So the way that I read it is also misleading, I would say. So here, even though I say I pronounce it as P of data given theta, but if the data is if in this case the data is fixed, and the theta is changing, then in this case, it is not a probability. It is something else. It is likelihood. So then to avoid this confusion, I give you the solution is to, instead of calling P of data given theta, simply call something else, call it likelihood of theta given data. So I can write it down here. So the solution is kind of just to do this, right? Can you see? I guess you could. So then it's clearer. So if the reality is here, this is a given, this is fixed, and then this is changing. So suppose this is a function. A function is fx. Fx means it is a function of x, and x changes. X is varying. And then here, this means this is a function of theta. So the theta is changing. Theta is the varying variable. So fx here is f of theta. Fx here is a f of theta. And then in this particular case, it is a function of theta given data. Okay, if I write this way, I guess it's easier to understand. And then less confusing, I would say. So another question is, would it make sense to standardize the likelihood to probability scale? No. If you standardize that here, then the entire posterior calculation is, you will get confused there. Yeah. But there is a scaling part. I can tell you later, but not here. There is a scaling part. Yes, there is. Yeah, but not here. Any other questions? Okay, another question is it likelihood in the sense of likelihood function for maximum likelihood estimates, or is it something else? They're the same. The meaning is the same. So here, the likelihoods in the Bayesian formula, the meaning is the same as in maximum likelihood estimation. It's the same. So now that you asked maximum likelihood, I can tell you a little bit. So let's focus on here, this one, this column, okay? This is the data. So let's say we do coin flipping twice, and then we observe one head, one tail. So this is the data. And then we want to estimate the parameter of theta using a method called maximum likelihood. So likelihood, as we know, is defined in this way. So it's really good that we have written this way. So likelihood is L as a function of the changing parameter theta given the data, okay? The data here is just 1 out of 2 times of coin flipping, and then the theta is changing. And since we know that the theta is a continuous parameter, it's from 0 to 1 and everything is possible, it's continuous. So what we can do is that we could imagine, well, maybe we do some small step. We can insert theta equals 0.01 here. We can insert theta 0.02 here. And we do it 100 times, right? Because if we divide it into 2 decimal points, 0, 1, 0, or 1, 0, 2, until 1, we will have 100 different numbers. And if we have 100 of these numbers, and we could use this formula to calculate the results. And then each of the results is the likelihood, okay? And then we can put all of the likelihood here in this column. So this column, they are basically the likelihood, given data is 1 and changing the parameter value. And in just a simpler case, we do not divide the entire 0, 1 space into 100 units. We just divide all of them into 6 units. So here it is 6 units. And then each of the column here, it is the likelihood of all of the parameters given this observation. And the maximum likelihood basically means you go through this column and then to find where it is the maximum number. So where it is the maximum number. And then in this case, the maximum number is 0.48 and 0.48, where the theta corresponds to a 0.4 and 0.6. Okay, in this case, this is the max. But in this case, we have only we have a equal maximum. But maybe if we divide this 0, 1 space into 100 units, you will find something like a symmetrical curve. And actually, in this case, the place where you will observe a maximum likelihood will be 0.5 if we do it. So then, to answer the question directly, here this likelihood, the meaning is the same as in maximum likelihood. You are trying to maximize the likelihood to find where the likelihood is the highest, and then to find what is the corresponding theta. And then this theta is the results, the parameter estimate results coming from the maximum likelihood estimate. I guess that's clear, right? Yeah, after this explanation. Cool. Other questions related to the likelihood? So if you are still confusing, I guess maybe some of you are. So a good place to go is to watch this video. And then this guy, in that video, and he explains the difference between the probability and the likelihood, okay? So I can already use this graph to say something. So here, there is a point, let's say there's a point. You can calculate the probability of something above this point. So then you could calculate the area under the curve, the integral, right? So then this area means the probability above this number. And then the likelihood, you can use actually the same curve because the entire distribution curve is the same. And what you do is that you put this point and then you calculate something here, and then this y-axis here, this means the likelihood, yeah. But if what I said is quite confusing, so just do go to watch that video, and I put the link here. And in general, this guy here, StatQuest, he explains many things very clearly, and including simple stuff like what is probability, and until some rather complex stuff like support vector machine and principal factor analysis. No, principal component analysis, PCA, some other stuff. And he has quite a lot of videos. And then if you have time, if you're interested, just go and watch. Do not have to watch all the other stuff, but watch this one. This is relevant. This is quite relevant to understand the difference between probability and the likelihood, okay? Yeah, I will send the slides as usual, just as usual. GitHub. Good. So after the P, I'll try to avoid saying that. Let's, after understanding the part of the likelihood, so now let's understand another part at the place of the denominator, okay? Another one is P of theta. So this is prior, this is easier to understand. This is just the probability of theta being something. So the prior is the prior knowledge, so something we know already before the data collection. It can be informative, it can be uninformative. It can be weakly informative. So if you read the literature, if you find, if anyone is using a Bayesian equation, if anyone is using a Bayesian modeling, they always have to specify which prior they use. So this, I plot two cases. So in this example, the x-axis says the mean time for one individual who smokes to develop a lung cancer, okay, just years. And then the y-axis is the probability density. So how likely they develop a cancer, a lung cancer. So an uninformative prior means, let's assume from 0 year to 100 year, every time is possible. So it is a uniform distribution. This is uninformative. This has actually a quite strong assumption in the sense that you see here, after 100 years, this is 0. So then this might assume that after 100 years, nobody could alive. So this could be alive. This is quite a strong assumption, honestly. But this part didn't make sense, right? This is a uniform distribution, so everything is possible. That basically means you do not have a strong preference a priori, so everywhere is possible. And another scenario in the orange curve is that this is a weakly informative case. So here, the majority part to the density is around between 0 year to, let's say here, let's say 60, okay, let's say 60. So the majority density is here, and there are some other density here. So it's more possible that this year to develop a lung cancer is between 0 to 6, and then the chance to develop the lung cancer after 60 years is a little bit less, okay? So this is informative because it has a slightly stronger preference here rather than relative to here. So this is the informative part. And what does it mean to be weak, to be a weakly informative? So assume that we know the peak is always here. The peak is always here. Is, let's say 20. The peak is always 20. And what we can do is that we can change the width to the uncertainty of the distribution. So if the peak, let's say the peak is here, we can have a wide curve. We can have a quite wide curve. Well, not here, not the other end. We can have a wide curve, very wide. So then the variance is high. We can have a more precise curve. That means it goes up and goes down quickly. So the majority of the density is around 20 in that precise curve. So that means we have a very strong a priori belief that 20 is the year, not something else. So then this is a strong informative prior. In that case, it is strong. But when the variance is larger, so the peak is here, but anywhere is it's also possible, even though here this is lower, but it's also possible. So then this is a weakly informative prior. Okay. Good. I guess this is easier to understand. So translating that to practical setup. So when we estimate a Bayesian model, so if you really have no idea what the value of the parameter could take, you just take a uniform distribution. If you have some knowledge of the parameter value, it can be from your prior experiments, from yourself. It can also be the results. The results are reported from somebody else. So if you do a memory task, and then the task is pretty much similar to what has been done from another group of researchers, so you can take some parameter results from their group and taking that one as your prior. And you can make it a little bit weak, right? So then if this is the results of the other group, you can make it kind of a weakly informative prior around the value you observe from the other paper you read. Good. And the denominator, it is the P of data. So here, there was a question about scaling to normalize everything to be within the unit range 0 and 1. So the normalization happens to the denominator, okay, here. So the denominator, the purpose is actually the P of data, here, the P of data. So the purpose of the P of data is basically to normalize the denominator, okay? So the denominator, so we know that this part, it is not a probability. This is a probability, but the product, because this one is not a probability, the product is also not a probability. And then we have to normalize that so that the left hand side of the equation is a probability. So how to do it? You just normalize it, right? Using P of data. And then the P of data, if we recall from the last lecture, P of data basically means is marginal probability. So P of data given all the possible thetas, okay? P of data given all the possible theta. So then this is a marginal probability of data, regardless of all the possible theta outcomes. So when it is a discrete parameter, it can be written like this. So the P of data can be rewritten like this. So this is something we have discussed already last time. And then when it is a continuous parameter, the P of data can be rewritten like this. Okay, so one is the summing up, the other one is the integral. It's something, it's pretty similar, honestly. Okay. And the purpose, let me just repeat, the purpose of P of data, the denominator, is to normalize the entire formula. So I will just repeat again. So here the likelihood is not a probability. Here the P of theta, it is a probability. And then the multiplication in this case is not a probability, but the left-hand side is a probability. So how to make sure they correspond? So then we have to normalize the right-hand side. We have to normalize the denominator by dividing the P of data, okay? So there is really no need to understand what the P of data means. So if we observe one head, one tail, we do not really have to understand what is P of observing one. So it doesn't really make too much sense. You do not even have to understand that. It's more serves as a numeric purpose so that the entire calculation meets the criteria of being a probability. So normalizing, scaling, so that the entire calculation lies between 0 and 1, and also summing up is also 1. Good. Any questions? Everything's all right? Or confusing? Yeah, no? Good. So next question is, so why the Bayesian formula or Bayesian theorem is important. So it is that, for example, if we know a coin, if I do have a coin here, so if we have a coin, so we know the probability of heads facing up. If we know it, if the coin is made by us, if we made by on purpose that the probability of facing up is 0.4. So if we know it, if we do experiment, if we do 1,000 times of experiments, we could expect that around 400 times we will observe a heads up, and around 600 times we will observe a tail facing up, okay? So this is something we know. If we know the cause, we can expect some effects, okay, good. But in real world, we don't know that the coin is not made by us, the coin is made by the factory. And what we can do is we can only do experiments. We can throw a catch, we can throw a catch, we can throw and catch, we can run experiments. And then we could obtain some data from running experiments, okay? So what we do is that we infer the possible parameter, how likely, what is the theta parameter, what is the probability of the coin it has that produces a head facing up, okay? So this is something we have to infer. So from effects, from what we have observed to something unknown. So this is what we do, right? It's the statistical inference. We collect data from two groups and then we compare if there's a difference or not. So we do a t-test. We use this statistical difference to infer if there is some possible cause between one control group and one treatment group, for instance. So if you see here, effect from effect to the cause, so from here to here. So what is that? That is basically this part. So we have the data and we have something unknown. So we want to know the probability of something unknown given the data we know. So this is just exactly the posterior, right? So if we do some analysis, we are basically trying to understand, always trying to understand the posterior of some experimental data or some survey data, doesn't matter, just data. So given the data, and we infer something unknown, the cause. Okay, so this is the posterior part. So then if you, so there's kind of a saying, it says that probability is orderly opinion and inference from data. There's nothing other than the revision of such opinion in the light of relevant new information. Cool. Any questions? Everything's all right? Still? Good. Okay, we have 10 more minutes. So let's just focus on the real world example, okay? Using this binomial model, and then this is the example from the Statistical Rethinking book. This example is quite similar to a coin flipping example, and then this is a little bit storylized, so you can see the difference. So you're now curious about how much of the surface is covered in the water. So the entire Earth, how much of the surface is covered in water. So what you do is that you cannot really go everywhere in the world on the Earth to measure the proportion of water, right? Because the Earth is too much and it's too big. It's not really too possible and economic to visit everywhere. What you can do is that you can go to a stationary store and you can buy a globe. So then if you buy a globe, okay, it's easy to handle. You can hold it in your hand. So what you can do is you will toss the globe up in the air and then you catch it. So this is like a coin flipping example, right? Similar idea. So what you do is that you will record whether or not the surface under your right index finger is water or land. So you have a globe in your hand, you throw it up and then you catch it and record under your right index finger, is that water, is that land, right? And then let's assume you do this experiment 9 times, and then you observe this sequence. So it's water, land, a few times water, land, and until here. So 9 times of experiments. And out of the 9 times of experiment, we have 3 times of land and 6 times of water. You could do some simple calculation. You can say, well, I just do 9 times of experiment and I observed 6 times of water. And what is the proportion? Okay, what is the research question? The research question is the proportion of water covering the entire surface. We could do a simple division. We could use 6 divided by 9 and we got 67%. So this is something we usually do, right? And this can be treated as a frequentist analysis. And what we can do if we can use the Bayesian equation to estimate the probability of different proportion given that we observe 6 times of water out of 9 times of experiments. This is our goal. Our goal is to analyze the same thing under the Bayesian framework. Okay. And before we do some real analysis, and I don't think we have time to do the analysis, but maybe it's good to give you a bigger picture of what can be done. So what are the steps of doing any kind of modeling? It doesn't have to be Bayesian. It's not necessary. So the most important thing is to have a data story. So data story means think about how the data might arise. So what is the data generating process? So it can be descriptive, it can be even causal. So the data story is important, right? So if you do an experiment and then the participants sometimes choose A, sometimes choose B. It depends on your experimental condition, and you might just wonder what might be the process that has driven them to choose A, that has driven them to choose B. So the data generating process. So again, think about how the data might arise, so the data story. So when you have the data story, you will just have to update the model. So educate your model here. So educate your model by feeding it with data. So then this follows the Bayesian update if you do Bayesian modeling. So you update. So you have a data story and you have some prior, right? So the data story is the model and you have some prior. And then up to this point, you only have an assumption of the data story. You assume the data might arise this way. And then together with the prior, you educate your model. So it follows the Bayesian update given the data. So there are data now. You update the prior and the model given some coming data, given the observed data. Because we are interested in the P of theta given data, right? We have to consider the observations. After the observations, what is the probability of the parameter? So here you educate your model by feeding it with the data, you do the Bayesian updates. So update the prior in light of the data to produce the posterior. And so here the updated prior then becomes the updated posterior, then becomes the prior of the next updates. So I guess this makes sense, right? So in the sense that you have a data story, you have a prior, and then you do one time of experiment, one trial, and then you use this one trial of the data to educate your model, and then you have a posterior. And then the posterior becomes the prior of the next trial. And then you use the data from the next trial to educate the model. And then this goes on for a few times, as many as the number of your experiments, of your trials. So this goes from the beginning to the end. It's always that the posterior from the current update will become the prior of the next update. Okay. You can basically imagine that yourself from tonight will become the new yourself of the next morning, something like this. Good. And then after this, there is an evaluation part. So here you have to evaluate. So you have a data story, you give the data to the model, you just fit the model to the data. So here is basically the data estimation part, the model estimation part. You have a model, estimate model, but the model might be imprecise, might be imperfect. So you have to evaluate it. So you have to compare your model with the reality, right? And then if the evaluation says, okay, the model works well, and then you could say this is a good approximation to the data. But in another scenario, if the model kind of does not capture some important feature of your data, then the model is subjective to be revised, subjective to revision. So here then, if the comparison says the model does not really reflect reality, go back to revise your model. What does revise your model mean? Revise your model means to have another data story, another data generating process. So you have another model to have in mind, and then do the thing to go through the steps here. Yeah, there's a question. So what would be the posterior in our case after throwing the globe one time? Yeah, you will see that on the next slides. Other questions? Okay, so you will see this quite often until the very end of the semester, okay? So what we do is, this is a simplified workflow of doing kind of statistics or kind of modeling. So we start from here, we have some data, and then what we could do is we could clean the data. Clean means if there is missing trail, something unrelated, redundant replication, and we have to adopt the duplication, we have to remove it, some data cleaning and reshape, and maybe do some exploratory analysis. And then here, this is the model part. The top part of the model is the data story. So the data story is the one I said, what is the data generating process? What the data might arise? So this is the data story. And what you do is that you feed the model to data. You link the data and the model. So here you do parameter estimate. You can do it with multiple algorithms. But here in this seminar, we will focus on the Markov chain Monte Carlo, the Bayesian part we will talk about next time. And then here is to evaluate and then to revise your data story. Okay, this is the same idea as what I have written above on the previous slides. So this is the same idea. Okay, so the data story, what can be a data story of the globe example here? We can assume, we could assume that there is a true proportion of water covering the globe. So the true proportion, we say that's theta. And we can also assume that the single tooth of the globe has a probability of P of producing the water. I think this should be theta. Yeah, good. Okay, so the true proportion of water covering the globe is theta, and each of the tooths following this theta, right? Each of the tooths, they follow this probability, the theta of producing a water observation. And obviously, it has a probability 1 minus theta to produce the land. So that's the opposite. Theta water and 1 minus theta, that's the land. And we also assume that each of the tools, they are independent of each other. So toast the globe and catches the result does not affect the result if you do it on the next time. So these experiments, these toasts, they are independent of one another. They're independent of each other. So those are the assumptions, okay? And the components of the model is, as I said, the likelihood function is the data story. So the likelihood part is the data story. So this is the same as the coin flipping example. And then here it follows the binomial distribution. So here, this is the likelihood part. And then in this particular case, this likelihood is a binomial function, okay? And then this binomial function, it has 3 variables. The one variable is here, the capital N, the total number of observations. In this case, we have 9. This is 9, right? This is 9. And then the W here is the number of water, so 6. We have 6 times of observations here out of the total number of 9. And then this theta parameter, the theta parameter is the unknown parts that we're interested in. So the proportion of, the true proportion of water, okay? Cool. And if we summarize that a little bit, we can say, we can just divide those 3 variables into 2 categories. One is known, the observed part, the other one is the unknown. So here it is the known part. We know total number of experiments. We know the total number of water observations. We do not know the theta, and this part is the unknown parameter. Okay, so this will be the last slide of today. And this directly answers the question of Jakob, I guess. He asked, what would be the posterior in our case after throwing the globe one time? Yeah, so here, this is the results. This is the answer to that question. So here we have this graph on the x-axis. This is the theta, okay, all the possible thetas. So theta is unknown. So between 0 and 1, all the values are possible, can be a possible theta candidate. And then here on the top, this is the sequence of the globe poses. Water, land, da, da, da. Okay? So after one time of water, that dashed line, this is the prior. So we have a prior. Prior, in this case, just indicates everything is possible. It is a uniform prior. So after one time of water, after one time of water, this update goes from here to here. It basically says, well, maybe the entire world is covered by water if you do just only one time of experiment. And then this changes if you have more observations. So the second time, the observation is land, okay, land. You observe two things here from the graph, from the figure. So here, this is the previous posterior, this line. And it becomes the current prior, right? The dashed line. And then after this second observation, it changes from the dashed line to this curve, to this solid line curve. This is the current posterior. So after one time of water, one time of land, water, land, you say, well, I try to draw some inference from only two times of experiment. One time is water, one time is land. Okay, so what is the current posterior? Maybe centered around 50%. Okay, so this is the results. Okay, centered around 50%. And then you do another experiment, another trial. You observe one more time the water. Okay, good. One more time, the new prior here, the dashed line, is coming from the previous posterior. And because we have observation of another time of water, so this curve shifted a little bit more towards this end, the right-hand side of the curve, of the figure, of the graph. Good. So you do this iteratively, and you do this here when we observe 4 times of globe toes, and then 5 and 6, and here to the very end of the toes. Okay. It always follows the same rule. So the current prior is the posterior from before. And then you take into account of the data observation, and then you draw a new posterior distribution or curve. So then that is the inference. So the very last observation is this one. So this solid line here, this is the overall posterior curve given the entire sequence of the observation. Okay. And after this, you might want to draw some conclusion, right? This is what we always do. So we can draw, well, actually order doesn't matter. This means if you shuffle the order of this sequence, the intermediate step, it will change definitely, but the overall results, so this solid curve in black, it will always be the same. So the order doesn't matter. It can be water, 6 times consecutively and 3 times of land at the very end. It doesn't matter. This sequence will also produce the same curve, posterior curve. Okay. And if we have this posterior curve, we can say, well, where is the peak? The peak is here. The peak is here. The peak is actually 2/3, so 6/9. But if you have this curve, you can also conclude that the others are not ruled out. What that means? So 2/3 is the most likely theta. This is the proportion of water covering the entire surface. But what if the true theta is 0.5. So what if the true theta is 0.5? Can we still observe this sequence? Can we still observe sequence? The answer is actually yes, right? Even the true theta is 0.5, out of only 9 times of experiment, it's quite possible that we observe 6 times of water and 3 times of land. And but it is relatively less likely than if we have a true parameter, true theta of 2/3. Okay, good. Yeah, so that's the conclusion we draw here. There are questions. If people have to leave, yeah, go ahead. This will be recorded, so don't worry. So one question, is the peak exactly 6/9? Yes, it is. It is. And another question, could you maybe give another short explanation which influence the prior has in the series? Okay, which influence the prior has in this series? For example, if we did not update the prior, would it just end up with the frequencies analysis? So here, because we have a flat prior, this makes the results here correspond to the frequencies analysis. So if the prior here, this one, this uniform one, if this prior is something else, we will not have the peak at 6/9. Okay? I can give you example here, but we cover this next time. So this is the prior we used. So this is the curve, this one here. This is the curve after 6 times of water out of 9 times of experiments. So the likelihood part is always the same, honestly, okay? But if the prior is something like this, so then the posterior shape will be different. Okay, and if the center of this prior is somewhere here, and then you will be likely to observe the new peak after the data is also here. Okay. Yeah. Other questions? The exercise part doesn't matter. We have to do it next time. Questions? Comments? So just one short comment from my side. So if this seems confusing for you to understand, I think it is for some of you if you have never heard about this kind of framework to analyze the data. So go to the book. So here, go to the book. It is chapter 2. I said it last time, right? So maybe if you have time to read the chapter 2 of the rethinking book. So here you will see more explanation of the same example. And then if you have confusion regarding the difference between probability and likelihood, first step is to go and watch the video I posted. So there's a link. I will send you the slides. And then the second place to go to is to read this student guide of Bayesian statistical book by Lambert. So there he also explains the difference between probability and likelihood. But that makes everything clearer. Good, I guess. If no more questions, and then I will just, we can just finish and see you next time, okay?